9, 8, 7, 6, 5, 4, 3, 2, 1, go.
So we'll be starting in 2 minutes. All right.
Yes, you are audible. Thank you.
A very good afternoon to our esteemed guest, faculty members, and all the students present here. My name is Divyendu Ganguly, and I'm the chair for the IEEE Power Electronics Society at KIT University. And I'm also serving as the secretary for the IEEE Student Branch here at KIIT. Just a few, things about KIT for our esteemed guest here, who I'll be speaking more about in a short while. KIT University is at the at the eastern coast of India, and it's one of the largest academic institutions in India, with over 30,000 students studying. And the IEEE body, talking about that, the KIT IEEE Student Branch is one of the most active and the largest by student body, and by the number of student branch chapters, we have 17. And on the very gracious occasion of the IEEE Day, we have an entire lineup of events throughout this entire week until next Sunday. And I'm really excited to welcome all of you here to the very first technical talk and guest lecture of the IEEE Day, the University of Southeastern Norway. And he has earned his PhD from the prestigious University of Bologna, Italy. His contributions to the world of electrical engineering are truly monumental. He has authored over 750 scientific papers and is a fellow of multiple esteemed institutions, including the IEEE UK and the European Academy of Sciences. His exceptional work has earned him global recognition. Most notably, he has been consistently ranked among the world's top 2% scientists by Stanford University since 2019. This year, he's also the recipient of the prestigious IEEE Systems Council Outstanding Service Award 2025. Sir, it's an absolute honor to have you with us today. I see our advisor, sir, Dr. VVS Kumar, has also joined, and he has been a monumental force in guiding us and always advising. The PELS chapter here at KIT University is very active. We're engaged in research and development work, and all of that he's handling, is advising really well. I'm so glad that we have the opportunity to have you as over here. I think VVS sir has joined us, but he's on his way to Spain at the moment, I believe. So, sir, are you able to speak right now?
Yes, but my signals are very weak. Okay, I can speak. Little. First of all, thank you, sir. Thank you, Kumar, sir. Thank you for accepting our request to present your guest lecture on.
I think, sir, there's some issue with your network. Uh, as you said, we're not able to hear you quite well right now. Should we start with the lecture and then? Uh, all right. I think sir had told me that this would be a problem with his network, and he said that he'll be joining a little later. Without any further ado, sir, we should start, and we're really excited to hear you. Please welcome Sanjeevi Kumar, Dr. Sanjeevi Kumar.
Thank you very much, KIT University and my colleague, Dr. BVV Kumar. Thank you for this invitation on the IEEE Day for Power Electronic Society presentation with your chapter. Also, thanks to Gangli for giving a brief introduction about me. Today, I like to give a technical talk on my research activities which are carried out by my students for several years. Before I start my presentation, could you please confirm my slides and audio are reachable to you all?
Yes, sir. Loud and clear.
I'm basically from the University of Southeastern Norway, and this is an overview how Norway country is located, can be a vertical or horizontal. I am exactly locating in a region called Telemark. From the Faculty of Technology, Natural Science and Maritime, we call it as a TNM. And about the university, we are located on the southern eastern part, having 8 campuses. I am from the city called Porsgrunn, where we have a campuses on engineering. University of Southeastern Norway became a full university in 2018, having 8 different locations, as I said, serving around 700,000 citizens, 4th largest university in Norway, and we have been collaborated with various industries, global players in the market, public sectors, and we have students from across the globe. Our department is electrical engineering, information technology, and cybernetics. We have bachelor programs, master programs in electrical power engineering, IT and automation, and PhD programs in electrical power engineering for 3 years. So these are some of the areas which our department is focused towards: marine technology, climatic changes, process control instrumentation, electronics, and of course, environmental impact on water, etc. Our research developments are focused towards onshore, offshore renewable energy systems like hydropower plant, wind turbines, bioenergies, photovoltaics, which are focused towards societal challenges. We are having a big research center, which is in Norway, is in Tough. Kelda is our company. Equinor is the largest offshore developer, and Skagerak Energy or local our energy partners. ABB is our industrial partners. Of course, we have local municipality, which is Porsgrunn and Skien, are our partners in the projects. So these are some of our facilities where the students are working in the theoretical background in laboratorical validations, which suits the industrial requirements. These are some of the test benches which are collaborated with the industries for making process control and automation integrated with advanced softwares. And we also have research and developments. Just hold on a second, I have a call. I'm sorry, there was an important call from the department. Could you able to hear me now?
Yes, sir. Absolutely.
Okay. Okay. So we are working closely with the industries. Our research groups are focused on electrical power engineering, renewable energy technologies, control designs, and we also have research groups on modeling and control focused towards water treatment process, hydropower plant health monitoring systems, flood management controls, etc. And of course, we work for sensor technologies in offshore for oil and modeling, drilling, etc., protection issues, building energy modeling and control. These are our groups. We also have applied modeling and control where work for smart cities, smart buildings, and smart maintenance in the industries by using advanced IoT sensors, industrial ITs, digitalizations, data analysis, data-driven model, and machine learning algorithms. All these details are available in the university website. I like to talk today on power electronics, which is my area of interest, in particularly the inspired power electronics topics in renewable energy systems, which includes fuel cell technologies, wind turbines, and photovoltaics, and few batteries, etc. So if you look at the transportation systems, we are moving more towards electric vehicles. When we are moving towards more electric vehicles, it also depends on the renewable energy system integration within the vehicles or for DC charging infrastructures. So in this case, power electronics converters play a critical role. We develop many DC to DC power electronics converters in orientation with industrial requirements and modifications, and we propose many solutions based on the developments and application required. Why we are moving towards more electric vehicles with fuel cell? Because it has a more power capacity, like small 1 watts towards 100 megawatt capacity. Temperature can be between -20 to greater than 800 degrees centigrades, applied for small power application or large power applications. For example, alkaline fuel cell, which is popular in the market, but recently proton exchange membrane fuel cells are much more popular with fast responses. So for example, alkaline, it can be adapted for high power applications, example large electric vehicles like trucks, bus, marine transportations, and this can be used between the temperature 0 to 80 degrees centigrade, and this can be adapted for the capacity less than 140 meter watts per centimeter square, which is pretty good scales of destination. Of course, it can go up to 10 to 200 kilowatt capacity. So the power scale is very high, temperature limit is very high, and of course it can be adapted for large power scale. For example, if you are going to use phosphoric acid fuel cells, these are adapted again for large scale, but the temperature scale goes up to 300 degrees centigrades, and this can be developed for minimum 1 kilowatt capacity to 10 megawatt capacity. So we have power rating variations. Of course, we can go for a high temperature application. So that's why fuel cell has a big market today's electric vehicles. So if you look at electric vehicles, we have fuel cell storage tank, then to the fuel reformer, then we generate DC power from the fuel cell. But the fuel cells efficiency are limited by 60%. So as a power electronics engineers, we are designing on power electronics converters, which are integrated stages from low DC to high power DC, then back to AC voltages for driving the propulsion motors within the vehicles. If you look at the efficiency, minimum requirement is around 80%, which can be ensured from the power electronics converters to the maximum 99% by the advanced devices and control. And of course, for the luxurious needs within the vehicle, it also can be done from the DC-DC converters. But hydrogen alone is an expensive generation, and in order to reduce the cost optimization, we are using hybrid modules. In the hybrid modules, we can have batteries along with ultra capacitors, because batteries has the limited lifespan and it can be used only for maximum 8 years, but depends on the road conditions, it can be easily deteriorated. Whereas battery also has a slow transient, it cannot pump the power out very fastly or charge the batteries very quickly. So it has a transient effects. and state of the charge needed to be maintained. But ultra capacitors or supercapacitor doesn't need to have a state of the charge, and it can be able to pump the power in a high rate, frequency rate, less than 5 milliseconds. It can be able to pump or discharge or able to charge. So this is a very big advantage of using ultra capacitor. So a proportionate model is very effective, like 15% batteries, 25% ultra capacitors, and 60% main powertrain from fuel cells in the market for a large scale or small scale electric vehicle in the future, where power electronics converter can be able to provide an effective solution. Because when you're applying the brakes, the regenerative energy available from the motor will be wasted. It can be pumped back to the battery or supercapacitor. We can able to store through power electronics converters. For a large-scale electric vehicles, it becomes a DC microgrid. We have to have a DC microgrid within the electric vehicles. Batteries goes around 700 volt capacities, and we are also having 25 kilowatt capacities of luxurious needs within the vehicles. Of course, a vehicle cannot be free of AC power supplies or AC loads, which can be around 20 megawatt capacity. All these can be done from electronics converters very effectively, keeping the minimum target of 80% above efficiency from the available integrated systems. So we have developed many electronics converters for high powertrain on the basics of Ned Morgan textbooks or any other textbooks you follow in your course modules in bachelor's. You can able to know what is an isolated and non-isolated converters. So we have non-isolated converters where input and output port can have a common ground, or we can have a ground on the input port and output can be floating model, or we can have a common ground between the input and output port with multiple stages of integrated components. Similarly, we can have a multi integrated components of the electronic circuits where input is ground and output can be floating. On other side, we call it as an isolation converters. Isolation converters, other name is the resonant converters or high frequency coupled inductor converters. So where we have again the same structure, we can have ground on either side on the input or output alone floating, or input and output can be having a ground but integrated with multi stages of components to have isolations. Similarly, we can have on multi-stage isolation converters with ground on the input and output as a floating. This is the overall scenario of converters which are available from the literatures because or basic studies. In power electronics, we can't avoid two concepts. One is a series combinations or parallel combinations. So all the converters what we design basically based on series parallel approach. If you look at very basic versions, we have power electronics converters where we have boost converters where the device is connected in parallel through an inductor where the output voltage is greater than the input. And if you look at here, it has a common ground. The ground is common. If you look at another configuration where we have a buck converter where the device MOSFET or IGBT is in series with the supply and the output voltage is less than always the input. And here also you can have a look the input and output as a common ground. Other possibilities we can have on a third configuration where again it is a buck boost converter where the output voltage can be greater than the input or less than the input. Here also you can have a look both the input and output are grounded common. But in case of D, you can have a look. We have shifted the diode from the forward bias to the reverse biased in the ground line. You can have a look. Then these are called floating grounds. So now the input and output are isolated by a diode. So they are become a floating model. So in this case, your output voltage and input voltage will have the same characteristics of a boost converter, but input and output are not having a common ground. They are in floating mode. Similarly, if you look at the standard buck converter, we can make it as a floating model by shifting the inductor from the forward bias to the ground point. You can have a look. Now the input and output are isolated. It works like a buck converter where your output is always less than the input, but now the input and output are isolated or floating. Third version, in a buck boost converter, we are shifting the diode from the forward to the ground point. Again, here we are making an isolation between the input and output ground. So it's become a floating converter. So these are the basics you might be studied in power electronics applications. What are the limitations of the proposed converters? There are a lot of limitations because you can't able to use the renewables which are connected like batteries on the input side very effectively with minimum duty cycles or duty ratio or conduction angle. So we have to go for the maximum value. It can easily cause the damages to the devices and reduce the power density and efficiency. To overcome all this, as I said, we can go for a parallel combination. You can have a look here. The converters are cascaded in parallel model, or it can be added in a series module. We can able to get a high voltage power conversion stages based on devices or based on a semiconductor device and based on passive components. So our approach is based on passive components, how to integrate and bring a high voltage converter based on industrial application requirements from the basic configurations. So we developed some converters based on a switched capacitor model. This is the basic version. You can have a look. We have two diodes, which has a two diodes and two capacitors. If you look at, they are going to conduct, then they are short circuit by means of diodes. Then these two capacitors will become like a parallel module, so we can able to add up the voltage. It's a very simple operation. So based on the switching, these capacitors will generate the energy or stored voltages. That's why we call these capacitors as a switched capacitor module. And there are many configurations. You can have a look how we can able to generate voltages based on switchings by using controlling the diodes or by using MOSFETs. You can have a look, or IGBTs. Here we have an advanced module where 4 IGBTs or MOSFETs is connected across one capacitor. So we can able to store 4 different levels of voltage in the capacitors, and we can be able to deliver to the load side. So that's why these converters, by using switched capacitors, we can able to bring in high voltage applications for the requirement of microgrid or charging unit is possible. At the basics, as I said, it can be cascaded in parallel module or it can be cascaded in series version. We also worked on a switched inductor module. Why we call it a switched inductor module? Because during the device is turned on, the inductors will get energized. When the device is open, the instantaneous energy will disappear. This is a factor of the switch inductor. So if you look at this case, we have 3 diodes for the current flow. When the device is closed, we are energizing L1 and L2. When the device is open, they become series. So in the series combinations, we get add up the voltage. But we have other configurations like this. You can have a look. For example, this case, you will charge L1 when the device is open, on. When the device is open, it will be delivered to the capacitor C1 for both the cases of L1 and L2. Then we have a high voltage on the capacitor to deliver on the load side. So these are some of the example where we can use inductor alone along with the load capacitor, or we can have capacitors along with the inductors to store the instantaneous energy. For example, here, if the device is closed, we energize the inductor L1, L2, and L3. When the device is open, the instantaneous energy, the voltage and current will be delivered to the capacitor, and it will be stored in the capacitor C2, similarly in C3, similarly in C4. All these capacitors again in parallel operation, so that the voltages will be added up and we deliver to the load side as a high voltage. So that's why we call it as a switched inductor module. Then we also worked on multi-stage converters, which are large configurations by adapting different structures. You can have a look. If you have a standard boost converter, is a high voltage converter, or the output is very high comparing to the input, or we call it as a step-up DC converter. If you look at on the integration with the load, we have include block sets, and these block sets are switched capacitors. So we have capacitors along with the flow of control by the diodes. Then we extend these blocks in series. You can have a look towards the load. So each block we have designed for a particular level of voltage increase from the output of the boost converter. Then we pump as a high voltage requirement for DC microgrid like 400 volt, 800 volt, or 1200 or 1600 volt in the future. Other parts we can able to cascade different converters. You can have a look here. We have a converter which is basically a boost converter. 2 boost converters are merged in combination with 2 buck converters. So this is on another approach. Again, we coupled with switched capacitors in blocks. So these are some of examples how we are generating multi-stage voltage generation for high voltage application. For example, this case we have a multiplier, or we call it as a this configuration. We call it as a Cockcroft-Walton method. These are all configuration. If you look at here, we have a boost converter. On the load side, we clamp the voltage by using capacitors, and the flow of current is controlled by the diodes. So these capacitors will clamp the voltage from one level to another level. That's why we call it as a multi-level DC to DC converters. And such configuration are available in literatures, but we done a lot of modifications, introduce our own modules of switched capacitors, and we propose all these Cockcroft-Walton multiplier circuits to integrate in DC microgrids and charging units. In a comparison, we worked and developed many switched capacitor family. We developed our own switched inductor family. We also developed multi-level converter family. We also developed XY converter family. We compared with the existing standard solution, which is called transformer or coupled inductor based converter family, which is a resonant converter. If you look at the reliability is very average, cost is very high because of the design of high frequency transformer or coupled inductors. And we have efficiency obviously very high because of the power transfer. Since it has a high frequency transformer, you can able to change the number of taps so that we can able to change the voltage transformation ratio from low to high, or it's very easily tunable. And by using soft switching methods for controlling the voltage and current, dV by dt and di by dt, you can able to produce a good power quality on the load side. The disadvantage is the structure is bulky. You will have more magnetic losses, and the application is only for heavy duty or high power applications. But the converter, what we develop for capacitors, which are called switched capacitors, switched inductors, are applicable for low power applications. What we develop multi-level converter is applicable for high duty way applications. Combining our own converters, what we develop, XY converter is a unique advantage because it has a high reliability, because we use only one switch and it is extensible structure by using many diodes. That is a disadvantage, by which we produce more discontinuous current. But the cost is average, efficiency is good, and it can be adapted for low or high power vehicles. So these are the summary which we develop our own powertrains, and this is another example how we work with electronics converters. If you look at this converter is a half bridge inverter, or in the textbook you might be studied as a semi-controlled DC to DC converter. So the same configuration we use for AC application as well as DC application, where we will have only one leg with two devices. So in DC to DC converter, we call it as a semi-controlled half bridge converter. In inverter, we say is a half bridge or one bridge inverter, H type. Where on the load side, we clamp, you can have a look how we are clamping the capacitor banks, and we call these banks as a switched capacitor, because based on the switching, these capacitors will store different energy from the midpoint as well as from the positive terminal of the supply. And these voltages will be added up and delivered to the load side as a bulk. And the most interesting advantage, we are not having more devices like MOSFETs or IGBT, only two maximum. And we can able to control these devices very effectively with the digital processors to control your AC grids or AC motors. Of course, we can integrate local batteries. If you look at this configuration, if you are going to use number of stages is 0, you are not going to get the number of devices also 0. I mean the capacitors and diodes. For example, if you are moving to the stage 6, if I want 6 level of increment, then I'm going to use 12 diodes and 12 capacitors. For example, if I'm going to use 3 stages, 6 numbers of diodes and 6 numbers of capacitors is required. If you look at overall gain, how much it can go to the maximum gain can go near to the maximum duty cycle. I can able to achieve the maximum value, and it looks pretty good in case near to 90% of duty cycle. What is the future? It doesn't have any magnetic circuits, so we don't have a transformer or inductors which can create magnetic losses. Input current always continuous is an added advantage. Even in the failure conditions, the reverse current will not flow towards the supply from the blocks, but from the devices, we have to be pretty cautious. And these are very easy to clamp up by using the blocks to increase the voltage. Since we have only 2 devices, the operation is very simple. So what are the challenges in the future we are going to face, particularly on electronics application in general, for renewables or for EV applications? So we have to improve the efficiency. That's a big challenge. So what are the mechanical parts which are available in renewable power generations, or in case of electric vehicle, for example, hydraulic shaft? These needed to be replaced by electric motors so that the system will become more electric. And today, for example, Norway has 95% plus electric vehicle, one of the fastest adapting country in the world for EVs. The reason is to provide green energy. So in this case, batteries and fuel cells will play a critical role in increasing the efficiency by integrating high voltage EVs. All these efficiency purely depends on the selection of electronics components. What type of semiconductor devices you are going to select, diodes and capacitors, of course, control strategies and EMI filters. How to increase the durability of renewables or electric vehicle? It can be done, for example, in renewables battery. Batteries, how it is charging and discharging, so all depends on the DC-DC converters, its ripple factor on the input side and output side, the distortion factors that can ensure very effectively the power flow and even during the hazardous conditions of the batteries. So these all decides by the lifespan of the components of the electronics components, what you select for semiconductor devices. Of course, the electric vehicle will have a lot of vibrations and thermal conditions. These all needed to be controlled by the electronics converter by its characterization, of course, the cooling methods. Other challenges always lies in selecting particular electronics converters which can able to provide you high efficiency, rigidness. At the same time, the cost must be small and size also needed to be small. This is a big challenge for developing electronics converters for the customer needs. How to increase the performances of the renewables or electric vehicles in operation? Because today we have a fast and very high speed power controlled industrial digital processes. So this all depends on the digital processor, how it's going to execute the given commands in a shorter time, so that the performance of the vehicle can increase or renewable integrated can be well ensured. For this, we have to integrate with Internet of Things, big data, machine learning algorithms, all need to be integrated in one platform for multi-vectoral control. Most important is the safety of operation of renewables and of course for the electric vehicle in standard. So in case of electric vehicle, the most important how we are detecting the faults in the stator, rotor, bearings, etc. by using IoT sensors without cables. So future deployments. Of course, we have security systems within the vehicle, which is called anti-brake systems and airbag systems. These are actuated by a small DC-DC converter, like coin in shape. I mean, the size of the converter is in coin type. So they are very effective to control all these production units in a faster time with the limited power scale from the batteries. So all these requires a high-speed DSP's dedicated system, how much it's going to respond with the predetermined programs. This is the future in the requirement on the side of safety. How to decrease the overall cost in the operation of renewable energy systems or electric vehicle, as the requirement of the customers are increasing, the luxurious needs. But how we have to reduce the cost by selection of proper electronics components, devices, digital units, etc. and sensors. So these all decides the cost to reduce the maintenance of your, and of course the reliability and high quality performance of the vehicles and renewables integrated. Finally, I like to conclude my presentation. The most important, the future scenario in case of electric vehicle is going to be fuel cells. Many research are going around to develop fuel cell based electronics powertrains, which fits very effectively for the vehicles for high power propulsion or of course for low power propulsions. So we have developed many power electronics converters on these concepts, and of course they are very cost effective. We use one MOSFETs or two MOSFETs, and we concentrate more on passive components, and we created now a modularity and controllability based on simple modulations and control. Of course, this all causes the reduction of the cost. We also develop many electronics converters based on multi-port configuration. I will show you with some examples where we can able to integrate multiple inputs, and we can able to deliver a constant output power. One of the easiest solutions by using power electronics converters. The most aim of our application is to develop electronics converter for low cost, eco-friendly and zero emission and high power applications by integrating different power electronics converters. In these aspects, we have developed many solutions which are available in the test. Of course, in many publications, you can have a look how we have integrated all these converters. So, for example, multi-port converters. So, multi-port converters, if you want to look at the charging stations, the many literatures has addressed a conventional model where we have photovoltaic, wind turbine, batteries integrated by using 4 different converters. You can have a look. Then it has been integrated to the point of common coupling, which is required a minimum 400 volt. Now the scales are pumped to 400 to 800, 800 to 1200 and 1600 volts. Then we are charging the electric vehicles, feeding the power to the existing AC loads or to the AC grids available. But the number of converter stage increases, of course, the complexity in control. So we develop our own multi-port converter. You can have a look. There are 3 input to the same converter, and the output are integrated to the common point of coupling. So you can have a look here. The level requirement for the wind turbine is reduced to 1 stage, whereas here you require 2 stages, AC to DC, then again DC to very high power DC on the common point of coupling. But here we reduce 1 stages. These are the advantages of going for a multi-port converter. So how we develop this configuration? If you look at on the input side, which is a very standard buck converter, and we integrated with a very standard boost converter 1 and 2. This becomes a cascading model and controlled by using the diodes. You can have a look. And of course, this is another buck converter. So 2 buck converters along with the boost operation, we got a cascaded circuit. One is for dedicated for photovoltaic, another one is for the batteries, and the load we try to keep a constant voltage application. So here the advantage, we are integrating different renewables to the same converter, and we are able to provide a constant output power, which is controlled by maximum power point algorithm. If the batteries or photovoltaic or PV is fluctuating on either side to above the maximum or minimum below the maximum values, we control the devices very effectively by using the modulation and bring them always to keep at maximum power point. So the advantage, we can be able to share the power among the 3 renewable integrated systems. These are tested in a laboratory model because the prototype model of a battery is very important to integrate with vehicles from the renewables. So first case, we tested for a 60% duty cycle, keeping the photovoltaic module like batteries, 12.5 volt is generated. You can have a look, the load current and or very smooth, pure DC with around 24 volt has been pumped up. And we are looking at the currents of the inductor. They are very periodic, doesn't have any spikes, which ensures the reliability and smooth operation of the devices. Of course, the ripple contents are within the limitations. On the other aspects, we try to reduce the power from 60% duty cycle to 40%. And in a reverse mode, we pump the power to 30 and the output voltage pump back to the minimum value of 18 volt. Even during these conditions, the current through the inductors are very smooth and periodic. How we are developing all these systems in numerical simulation model, the efficiency goes near to 97% to 98%. Because it's an ideal environment. But in real case, around 60%, we are getting efficiency only 93.6% after all the switching, conduction losses from the devices and passive effects. How we develop all these control algorithms, we have sensing the parameters from the current, voltage, from the batteries, photovoltaics, and of course on the load side, output voltage and current. Then we give to a multi-objective controllers, which controls the power flow, which controls the battery, which controls the mode of operation, and of course duty cycle. What is the algorithm? We start the program, we check the power of the photovoltaic, which is greater than 0. Then we go to the next step, we check the power of the battery is greater than output power. Then we check the battery current is greater than the maximum battery current. Then we connect PV to the load. If fails in the first step, we connect battery to the load because photovoltaic is out of service. If we fail in the second step, there is a power from the photovoltaic, but that isn't sufficient enough to drive the load requirement. So we connect both battery plus photovoltaic to the load. If we fail in the third step, we check for state of the charge. If the battery has 90% state of charge, we connect to the load. If not, we connect PV to charge the battery, then to the load. So we also developed some other electronics converters based on our own synergies, looking at the industrial solutions. So if you look at very carefully on the load side, it's a very standard boost converter. On the input side, we integrated a half bridge, or I say is a full bridge inverter, where one of the devices is replaced by inductor LX, here inductor LY. Then we have three MOSFETs. We control at three different levels. That's why it's called a triple switch mode power electronics converter to enhance the capacity on the load side. When the device is open, we energized LX. When we close the device MOSFET SY, we energized LY. When the device is open, we transfer the energy LX to CX. We transfer LY energy to CY, and these two will become a parallel, and the voltage will be added up and deliver high power to the load side boost converter. And we introduce another diode here for the flow of current. That's very important. So always here the power supply will have unidirectional power flow from source to the load. So the input side is well protected under faulty conditions. And these are the applications we can able to go for to maintain around 800 volts or 400 volt. Now the scale increased to 1200, 1200 to 1600 volts. Applied for EVs, DC microgrids, DC home application, AC grid application by integrating fuel cells, photovoltaics, and batteries. Once the converter is designed, we are looking at the 60% of the duty cycle. The converter is able to provide 42 times the gain, but other converters are available in the market or literature studies are less than our proposed converters. Once the converter is designed, we are looking for the losses. That's very important. The MOSFET provides around the 16 to 17%, diodes between 4.8 to 5.2%, capacitor 6%, inductor internal resistance, which is around 9% losses. So you can have a look. We are generating near to 400 volt. It is not true 400. It's around 395 because we are switching conduction losses and passive effect losses. So all the losses is reduced. Then we are around 395 to 396 volts, and the voltage across the diode is always forward bias pumped to 185 from the battery modules which are connected on the input side. The voltage across the MOSFET is pumped to 185, and the current through the inductor is more symmetrical. It's not only important when we are testing the converter in the mode of constant power operation, but also regulation is very important. So we designed the converter to regulate in different levels of voltage from maximum to the minimum design values. All the cases, the input voltage which is connected to the batteries, fuel stacks, or photovoltaic doesn't affect. You can have a look with the minimum frequency signals are appearing with a limited ripple content. At the same time, the input current follows the load regulations, and load current varies according to the load requirements. So you can have a look. We pump the voltage from 395.2 volt to the minimum 206. All the cases, the input kept like a battery module around 30 volts, and the current through the inductors are periodically varied from 16.59 amperes towards 4.67 amperes, and the load current also regulated according to the demands. How we regulate all these in the closed loop operation? We control the MOSFETs. We have three MOSFETs. Two MOSFETs are conducting at 50% and 35%, whereas the third MOSFET always kept at 35. If you want to go for the third mode 206, we kept all the two MOSFETs conducting at 35%. So we have regulations by controlling the duty cycles. You can have a look. We are not using more than 50%. So we reduce switching losses, we reduce conduction losses, and it's very good for thermal effects of the devices and power density, because we are not using like a standard converters where we go near to 65% or 75% of the duty cycle. So it's just on 50% of the conventional applications. With this, I complete my presentation. Thank you for your attention. If you have any question, I'm happy to respond.
That was really, thank you so much. That was really insightful, and it was really easy to grasp. Most of, we are in third year, most of us here, and there are faculty members who have joined us here as well. Apart from the members who have joined us here, this is also being live streamed on YouTube, and we have viewers over there as well. I'm sure a few of our members have a few questions, so I'll open the floor for question and answer.
Yes,
Anybody?
well,
Yeah. Does anybody have any questions? All right. Well, I have a question. Oh, well, we see. Okay, Abhinandan, please go ahead.
Hello, am I audible?
Yes, yes, you are.
Okay. First of all, good evening, sir. I'm
good evening.
Abhinandan Singh. Sir, I had a question that what do you believe is the next major breakthrough we can expect in power electronics that will, completely change and impact the systems that we have today?
This is a very wonderful question, and of course, there is no limitations in research. I'm right. We don't have limitations now. We are working more on gallium nitride and silicon carbide device to be integrated in renewable energy sectors. Electric vehicles is one of the major challenges and cost reduction aspects on the topics of semiconductor devices. And other side, for example, I'm working on the projects where we are working more on offshore renewable energy technologies. We are talking all these grids in megavolt scales, but our electronics converters are limited to kilowatts. So we are have to go for high power applications where electronics converter needed to be worked for megawatt, extra megawatt voltage capacities. So we call it as a EHV configurations. Still, these configurations, our electronics converters are not really applied in transmission and distribution. So we are talking on fax devices, we are talking on shunt filters, we are talking on series filters, where these research are limited, not like infinite grid. So developing the semiconductor technology for electronics converters for high power application, we have a large space. One of the research aspects. Another aspects we have integrating various renewables, and we use electronics converters. Then who take care about the resilience and low inertia operations and self recovery. So we need to integrate the modern technologies of AI solutions, particularly artificial intelligence solutions, integrating IoT sensors. But there are big challenges comes when these semiconductor devices going to respond with drastic variation of integrating many renewables, because in the laboratory model, whatever I present, here we use one batteries, one wind turbine, one photovoltaic, but think about increasing the numbers in a large scale power system. Then how power electronics converters can able to cope up multi-dimensional, multi-vectoral, multi-power flow operation. These are the big challenges from us. On other aspects, current scenario, we are working more on power electronics converters, how to integrate with batteries for second life. So after 8 years, we are going to have more than several billions of batteries. So there are statistics, 350 billion batteries will be available in the world in 2030. And they are small devices, will be ideal during the night hours or parking conditions. So how to use these batteries very effectively by using electronics converter to integrate with the grid, so that each vehicle can become an entrepreneur. So that there is a big gap. Research cannot be stopped in electronics because we have to go for milestones. As the power capacity increases, we have to have different problems can come up at different stages.
Thank you, sir.
Anybody else? Sanidhi, please go ahead.
Hello, am I audible? Hello, sir. I'm Sanidhi Dev. I'm the secretary of the society. Thank you so much for joining us today for this insightful tech talk. I have a question because I'm personally interested in AI and ML. If you think there is any role of artificial intelligence and machine learning that are beginning to play in optimizing the control and efficiency of renewable energy converters?
Obviously, I didn't present today about AI control algorithms, what we developed in past 2 decades. Yes, as I said in my last word, self-recovery, self-resilience, operation in low inertia grids. These are big challenge. I'm right. We have to monitor. We have to use our digital controllers to perform to a certain margin. But with AI solutions, by using machine learning algorithms, the quick time we can able to grasp the fault, example I'm saying about fault, or we can able to, of course, pre-detect based on the information of currents and voltage and frequency, we can able to predetermine the faults. So these algorithms are compact in structure, but they have multi-dimensional freedom. Degree of freedom is very high to get optimized results in few seconds, I mean microseconds. That's why AI solutions are vital. For example, modern electric vehicles. In modern electric vehicles, by using GPS, you are able to control your driving systems. Of course, as I said, when there is a fault happen, you have a protection by using ABS or airbags. These are operated by AI solutions. And for example, in few years' time, we will have a lot of charging stations. And if you are on the driving unit systems in the roads, you don't know which station is free for charging or which station is available to charge your vehicle. So these all can be predetermined by using GPS and of course using machine learning algorithms and AI solution to integrate and get into one platform where you can be able to observe your requirements. Other aspects, if you ask me about renewable energy systems today in the world, I believe even in Norway, we have a very small percentage, not even 1%. The clean energy in Norway is around 99.9%. For example, the grid doesn't know the power is coming from hydropower plant or wind turbine or from the fossil fuels. It can be from coal power plant, etc. Who will monitor all this? So we need an aggregators. The aggregators are the computers, high-speed desktop computers. They're going to monitor all these parameters based on AI solutions. So we have optimization algorithms based on a different AI platform integrated into one computer, and each AI is dedicated for particular aspects of the application. And we can able to monitor how much percentage of renewables are coming, generation from wind turbine, generation from photovoltaics, or from fossil fuel. For example, in Norway, we have a live website from the government of Norway where you can able to find how much percentage of wind power is developed, how much percentage of hydropower plant is generating per second per minute. You can find it in online statistics and data. Of course, how much percentage of clean energy is produced, 99.9%. How these are happening because of the various optimization AI algorithms working parallelly. And big countries like our country, India, requires a time because of the size and financial requirements, diversity of the country. So as the vision of the Prime Minister, by 2047 or 2047, things will happen very quickly because Norway is a small country with a good financial background. Scandinavian countries like Denmark, Finland, and Ireland, they can easily develop to the next level from the policy making. That's why Norway has been a pioneer in renewable energy technology with the sustainable grid, because it has been deployed with AI solution to predict all these information in advance and available in a open source for the customers, of course, across the world.
Thank you, sir. I think we have another question from Ashish P on YouTube. He asks, uh, for students like us who are aspiring a career in this field, what specific skills or research area in third year and fourth year to really gear up for the corporate world, and what projects they should do in the society? He's one of our
Candidate, it's excellent question. If you, whenever I go for my lectures I work for many universities across the globe. So whenever I go for my lectures, I am basically a power electronics engineer. My background is on electrical engineering in bachelor's, master's is purely power electronics. My PhD is power electronics. So for other areas you want to travel with power electronics, I always say in my classroom, you have to be good in electric circuit first. The third semester, I don't know, in the second semester, you have to have your basic course, which is electric circuit. You have to be good enough. I mean, not outstanding, the basics, how to apply the circuits, equations, solving the skills, particularly with complex um, algorithms. I mean, complex theories, not like real problems. The complex problem means we use more complex theory, am right? Real part, imaginary part, we should know how to do that very quickly. That can help you a very good, strong foundation. The second is the control system. You might be studying in the fifth or fourth semester, I'm not sure. So the control system is very important because it is a part of the power electronics. Then power electronics. When you're very good in these three subjects, I think you could become a good power electronics engineers for the society. Apart from that, our power electronics is always termed as power electronics and drives, so electrical machines. So I recommend four subjects, which are power electronics, electric circuits, control systems, and electrical machine. You have to be very good foundation. Then I believe you are fully fit, and of course you have a good career, outstanding career in power electronics market. And about the job market, as I said, yes, today world is moving more towards renewable energies, fuel cells, on aspects of power, battery technologies. So you have a good job opportunities in these markets where renewable energy technologies are highly demand in India and abroad, particularly for wind turbines, batteries, fuel cells, and photovoltaics, where I believe next 50 to 60 years, the market is very big. You can work on these technologies by integrating power electronics. Apart from that, another market still very silent is the recycling of battery. Everybody we talk, everybody says we are going to recycle. Until now, there is no solution. All under prototype model of testing. There is no concrete evidence for say recycling of batteries until now in the world. Nobody says, yes, I recycled, I produced. There is no market, no evidence and policies or any regulation has been formulated for recycling batteries. So there is a big market. In India also, I've seen recycling, green recycling if efforts are done. So there is a big market. Of course, there are the plan for developing large fuel cell powertrain modules hub in India. So there is a big market. So of course, this market experience helps you all to also to move towards abroad countries if you plan your career in abroad. So market for electronics is consistent, and there is always a demand either in academics or in industries.
Thank you so much. That was really insightful. I think that's also a really good segue to what I was planning on asking. For all the students over here who are planning on doing, masters abroad, maybe in Spain, if you can just shortly, enlighten us on what the process is and how we should get started.
For the master degree, particularly for Norway, where I work in the Scandinavian country, the Norway, we look, currently we don't have a funding from the university. Before it was like, you don't want to pay for your university tuition fee, but now it's a tuition fee. And you need to have a minimum 6.5 your IELTS scores or 5.5. You can please verify in the website. So IELTS score is very important, and you have to pass the courses with the minimum requirement. Then you can apply. But this is not funded. If you want to find a funded positions, you have to look for Marie Curie scholarships, but it is very competitive. Many European universities in general, particularly in Scandinavian countries, we don't fund currently, but through projects is possible. For example, we have from Norway a funding called Woodfolks Norpod, where you can't get a full degree from Norway, but you can come for 6 months, 3 months, and you can do the projects. And this is a collaboration between UGC and Government of Norway. And as per the guidelines, the institution should be an institute of national importance for the collaboration. Otherwise, other means, if your professors are collaborating with us and if we have a EU Horizon or Indo-EU projects, where these projects will provide you the funding for your travel, stay, life expenses coming to Europe, particularly Norway in general. So if there are some funding mechanism arises, I will let you know through by email. But currently, if you want to come directly for a master programs, you need to go for you need to pay a 230,000, 2.3 lakhs Norwegian krone per year is tuition fee. We don't have funding from the government. Otherwise, it is the joint funding between your institution and with my university, or there should be a project.
Thank you so much. Thank you so much once again.
Visit also Ministry of, now it has been changed to Ministry of Education, where you can go and find, if you look at Norway, it's very difficult to provide fundings, but other European states like UK, Austria, Germany, they pop out a lot of advertisements. They have funded master positions, fully funded master positions. You can apply, but as I said, it's a very competitive. You have to be having a good grades. Most important is your IELTS scores, and apart from that, what is your extra activities? They also look, not only your curriculum. For example, you presented some projects in international symposiums, conferences. This makes you a distinguished candidate from others. So it's not only like I know I've got a yes grade in the subject, I got so much percentage. That's a part of the curriculum, but what you done away from that also play a important role for your getting this fully funded positions.
Thank you. Really good. Well, KIIT happens to be an institute of national eminence, and maybe I can go and talk with authorities to, if we can establish an MOU with the University of Southeastern Norway. I think that would be a great collaboration in the future. I think Dr. VVS Bhajana sir is also here. If he, yeah, please give the vote of thanks, sir. Sir, we were able to hear you, sir, then. I mean, your mic was working, at least. Hello, sir.
Hello.
Yes, sir, we can hear you.
Hello. Yeah. Thank you, sir, for accepting my request and to give and deliver a lecture on this IEEE Day celebration. Thank you very much, sir.
I wish
Hello.
you all great success, and thank you very much, Dr. BVS Kumar. Much appreciate for your invitation. Also to your secretary Ganguly for organizing a wonderful event. I wish you all a great IEEE activities in your institution, and fantastic. So of course your institution is hosting now IEEE System Council. Your colleague, I don't know, chair Dr. She's visiting Singapore, so it's always a good collaboration with KIIT.
Thank you so much, sir. Thank you so much for joining. Thank you so much for taking time out of your schedule to enlighten us with your knowledge. I'm sure for all of us, on behalf of all of us here.
I think Dr. Ranjita Patel.
Ranjita Patel, ma'am. Yeah. She's also visiting Spain as well. And then she'll be going to Singapore. Yeah.
That's great. See you all. Thank you very much.
Thank you
Bye.
so much, sir. Thank you.
Bye.